Hi. So this is the feedback control, machine tuning and optimization track, first part indeed. Tomorrow we resume the second part. My name is Enrique Blanco from CERN, Switzerland, and I'm co-chairing the session with Marco Lonza from Elettra, Italy. As you can see in the slide, for this first session, we have 3 interesting talks. And we may remind that we have 12 minutes for each presenter, 3 minutes for questions, and you can use, you can put your question either through the raise your hand or the WOBA question and answer. Okay, so I'm gonna answer now. So I can give the floor to Dr. Abdul Ewal. He is currently working in the National Museum facility of the Lawrence Livermore National Lab. His research interests are in automated optical alignment, pattern recognition, adaptive optics, optoelectronic computing, optical digital image processing, and neural networks. So the floor is yours, Abdul. You're muted. So maybe I can unmute you.
Yeah, this particular topic is related to the alignment of a specific subsystem of the NIF, which is known as optical Thomson scattering. And my co-authors are listed there. Let's see, my slide is not changing.
Is it blocked? Maybe you answer again.
The slide is not shifting to the next one. Let me see.
We will always see the same slide, the first one.
Yeah, correct. It's not changing.
Can you unshare and then share it again?
Oh, okay, unshare and share.
Yeah.
So one of the purpose of this optical Thomson scattering laser is to measure the plasma quality using a 5 omega laser light. And just like the NIF, every subsystem needs an optical alignment. So my talk is mostly concentrated on how do we align this optical Thomson scattering laser by processing images of the laser beam at different control points.
You still have problems, Abdul?
Yeah, let's see. It's okay. Oh, looks like I have to do the same thing. So basically, this is the desired. So this is one of the image of the beam where we are asked to find the detection spot at the center of this comet-like pattern at the head location. And this is the 3D cross-section of the beam. Maybe I go to the difference.
Otherwise, just share the slides, not in presentation mode, if that helps.
Oh, okay, let me do that. Is it visible now?
Well, it's really small because you share also the
Oh, okay.
Yeah, it seems working now. Now it's okay.
How it's working.
Yeah, so this is the beam and we are trying to detect the head of this beam. Normally for a Gaussian beam, what we do is we normally detect it by a centroiding method where we do a threshold to remove the background and then take the centroid of this largest blob. So when we apply this same centroiding technique, we usually apply a low threshold and we find that the detection spot is not really at the head. So what we have to do is adjust the threshold to 75%. And then we find that the detection spot is now in the head of the comet pattern. Now to test this particular centroiding technique, what we normally do is we do a stability test where we take a number of consecutive images and process them at the same time. Now, when we do that, what we notice is that we have a nice cluster and then there are two particular spots which are further away from this cluster, about 20 pixels. So it looks like it could be one of two reasons. One is the beam actually moved during those observation period, or there is a problem with the algorithm. Now, when we analyze those two particular images, what we notice is a normal image which looks like this. It has the peak at the head region. The image where the detection spot appeared to move is actually because the spot appears on the tail. And we notice that there is a smearing effect, and overlapping of two smeared image produces a maximum at the tail. So this causes the detection spot to move. So what we want to do is find a way to detect the head of this comet pattern in an intensity insensitive way. And the normal technique we usually use is that is used for tracking shape. It is called match filtering. Now, when we apply the matched filtering technique, what we find that those two particular images shown here in the middle row, they now detect the spot in the correct location. And it is no longer choosing the maximum location. Now, in order to test this new algorithm, what we do is we take 100 images at the same position without moving any hardware. If we apply the current technique, which is the centroiding, we get a cluster which is shown on the left, and it has about 7 pixel radius. Whereas when we apply the meshed filtering technique, we get a very tight spot. And 99% of the spots are within a very small radius of 0.3 pixels. Now, the second loop I want to discuss is slightly more challenging. It has these two diffraction rings in this horizontal location that we need to detect. Again, because this is a specific shape, we apply a meshed filtering technique where the template of representing the diffraction beam has this kind of pattern. It is a ring shape where part of the ring has been taken off. And this particular shape is defined by 4 parameters: the radius, the delta, which is the width of the ring, the size of the inner radius, and also a missing fraction. Now, in order to apply this template, what we normally do is we don't compare this template with the whole image. What we segment the specific part of the diffraction ring from the big image by knowing its approximate location. And then we apply mesh filtering. We detect the correlation peak, and we do a post-processing which defines the distance between the 2 points. Now, since there are 4 parameters, what we normally have to do is do an optimization to select these 4 parameters. So normally what we do, we have an image set of 100 images taken in an aligned position. And we try to run through all these images and see that if it can detect at the correct location. And it gives us a set of 4 parameters, and as shown in the lower left. Then we take these and then apply it to historic set of images in the NIF, which could be like last 1 year of images. And then if it has some failure, then we readjust the parameters and rerun this loop. So it takes a couple of about 20 hours or so of optimization to get a good set. And this slide basically shows the different parameter for the left ring and the right ring. And because they are different, these parameters are different. Now, sometimes what happens, these rings could be rotated also. So since, if you recall, in our first step, we segment the 2 horizontal sections, assuming the rings will appear there. Now they don't appear there. So what we need to make sure that if we do a detection, we have to again be certain that the ring is there. So we design a certainty detector, and what it is basically comparing a cross section of the detection position with the template. So the template is like a pulse shape, which is the ideal ring. And then we compare it with the cross section. And this comparison is done by an inner product. And I have a work called trinary inner product associative memory. And basically the inner product makes, when there is a match, very high positive value, and when there is a false detection, then it creates a very large negative value.
Abdul, you still have 2 more minutes.
2 more minutes.
Two more minutes.
The rings also moves with respect to each other. So basically all the parameters during alignment also changes. Now these are 5 different positions, and we take hundreds image set from each position. What happens is now the optimization becomes difficult, because instead of 100 position in one position, we have 500 images in 5 different positions. So we have to sequentially or optimize one set, then go to the next set, and so on until we come back to the first set. And so that there is no failure in any of these sets. And so this becomes more complex optimization problem. However, we also do a change of the template. Instead of a full circle, we take a half circle and extend the ring horizontally. With these 2 changes, we get a new parameter. And the main thing difference from the previous step is it has a reliability detector. And if any of the spot is missing, then we can predict it using simple trigonometry. And our result is in the using the first template, we get a result which is shown on the left, and on the right is the new template and the new optimized result. So basically I have described 2 different loops. In one case, a centroid based approach was changed to a template matching. And in the second case, a template matching is used, but it has to go through an optimization to get the correct results. And thank you. That is the conclusion of my talk. And if you have any questions, I'd be happy to answer them.
Thank you very much, Abdul. We have time for one question, if you have any. I haven't seen any raised hand or questions in the WOBA. I made you ask one very fast. Is that I read it that you mentioned that with this alignment, or with these results of image processing, you are doing some automated closed loop steps.
Correct.
Is that true? What
Yes.
is your criterion of stability?
Yeah, stability is like, usually we have a reference point. So it could be a point in the pixel of the camera. When the beam moves close to the reference point, then we stop aligning. So basically, gradually it moves close to the reference point, and then if it is within a certain pixel, then we stop aligning. and don't move any more hardwares.
Marco, you want to intervene?
Yes, just short. Yes, if it is time, one short question. So I guess this optimization is done online. So the question is, what is the repetition rate of data acquisition, so image acquisition, processing, and setting of the actuators? And on which hardware are you running this software?
Oh, okay. Yeah, so this is run on a Linux platform, and the optimization is actually done offline. That means when we run the software online, it runs with fixed parameter model, which works in different position. And the only hardware we are moving here is basically mirrors, like programmable mirrors, a pair of them, which changes the direction of the light.
Thank you. Thank you for your talk.
Welcome.
Okay, thank you very much, Abdul.
Thanks.
Okay, the next speaker is Giulio Gaio from Elettrosincrotrone Trieste, Italy. He's going to talk about a framework for high-level machine automation based on behavior tree. Giulio Gaio works at Elettra in the controls group since 2002. His activities cover the development of Tango servers, Linux kernel drivers, and real-time modules. He is responsible of feedback system for the stabilization of the electron and laser beams in Elettrosynchrotron and Fermi-free laser, as well as of systems for performance optimization and autonomous execution of complex tasks. Please, Gaio.
Can you hear me? Do you see my slides?
Yes, good.
So
today,
thank you for the introduction. So today I'm going to present a framework for the high-level machine automation based on the behavior tree that is currently in operation at Elettra and since 2019, and recently introduced also in the Fermi-free electron laser. So the automation framework is always a recurrent topic. If you do a search also in the Jackout database, you will find a dozen of these automation frameworks. Some of them for sure have been dismissed. Others are currently in operation and keep our beautiful machine running. Some others maybe are also trial. But I'm quite sure that this is the first time at the ICALEPCS conference that are not one, but two automation framework based on the behavior trees. So behavior tree is part of the large family of artificial intelligence. It's not machine learning. It's more or less a mathematical model for plan execution. And why? And something that mimics quite well the AI in automation framework, because probably it is the only way to achieve in our machine something that looks similar to full automation. But we are quite convinced at Elettra that before integrating day-by-day operations, machine learning, let's say, we must be able to transfer efficiently the logics that stay in the mind of the humans in the software. And then when we will be able to do so, then we will start to integrate also machine learning in operation. What does it mean, full automation, and how to measure it? For a user facility like a cyclotron, full automation means recover from a beam object and give a stable beam to the user without any human intervention, without intervention in the control room. The metric to measure a human intervention is the minimum interaction between the human and the computer that controls our machine, which is one click in a keyboard or a mouse in the control room during the user's tuning shift. So if you sum the click rate during the user and machine tuning shift, you get the automation level, which is 0 for an autonomous machine. So with this idea in mind, simply if you want to improve the automation levels with your machine, you simply have to reduce the number of clicks, which means to move the logic from the graphical interface, standalone scripts and standalone programs that run in our virtual and real control rooms to server-side application that in our case is our Tango server. To speed up this knowledge transfer, we have to involve for sure more people that not necessarily are professional programmers. In order to minimize bugs, we have to privilege configuration and instead of programming. And for the same reason, we develop a homemade scripting language that performs simple read-write operation, the control system, and implement if, else, and the harmful go-to statement. So the example, so this is the line, an example of so the developer, when he have to write a line of this language, has to define first the step number, then the logical expression in green, then he has to add the step description, then in error message that has to be friendly to the humans and that will be followed in the logs also with the error message coming from the control system. He has to set the timeout and then some optional, some instruction to catch the exceptions. And this is below in the slide. There is an example of a sequence based on this language that reset and turn on the power supply. So this language, let's say it's quite powerless, but so how to build up a very complex task with a so powerless language? The behavior tree are exactly designed to implement complex tasks starting from simple one. It is used by AI in video games and unmanned vehicle. And it is based on the one-way relationship between the parent node and the child node. The behavior tree are direct acyclic graph, which means there could be no loop between the child node and the parent node. In the most simple implementation, the parent node starts the execution of the child node and waits it to complete the task. If the child node goes in fault state, then also the parent node goes in fault. There are two types of nodes in a behavior tree. Those that perform a real action on the machine, so read-write operation, and nodes that are structural. For example, nodes that start a child node in series, child node is in parallel, invert the returning states of a child node, execute at least one child from a multitude, or simply execute one of the two child nodes depending on the condition. And all the nodes, the nodes that perform action and the structure are implemented in the same scripting language. So the main actor of the behavior tree, so it is a tree node that we call, without no fantasy, sequencer. Sequencer is a Tango device implemented a task. So when the sequencer, which is a Tango device, started its initialization, it loads the sequence from a text file from a Tango database. The sequence is composed in two parts. In the first part, the developer implements the logic for the task with the scripting language. In the second part, it declares the dynamic attributes that are useful for implementing the logic of the task. And these dynamic attributes are also mapped as a read-write dynamic attributes, so they are accessible from any client in the control system. The task could execute also MATLAB, Python, and Bash script, but is discouraged normally. The sequencer presents also a common interface to the control system, which is basically made by commands that are used to control the task execution and help the clients to build up the structure of the tree. So the client or the operator in the control room normally send a start command to the root node of the tree. Then the execution roll down through the tree till the bottom part. It is possible to, during the execution, stop, pause, or abort a node, or if the behavior tree is configured, propagate this command even down to the subtree. So we build, it is not possible to manage the big behavior tree with the standard the standard GUI is provided by Tango. So we build some graphical interfaces that are automatically generated by getting information from the Tango database and by dynamically exploring the behavior tree. In this case, this panel implemented with Qt Cumbia is connected to the behavior tree that implement the electrocyclotron autopilot, which detected a beam dump, recover the machine from the beam dump, reinject and give light to the user. This tree is made by two main subtrees, the one that recovers the dump and the one that inject and give light to the user. One in the middle with the root node that detected the loss and then execute in series the recovery and the reinjection. In total, the number of nodes of the tree is more or less 700 nodes. It's possible to zoom in into the tree.
2 minutes left.
And just it's worth to note that without implementing automatic optimization, it was not possible to get the same performance of an operator. By the way, it's not possible to execute continuously this behavior tree for safety reasons. So after being dumped, the operator has to do one click to start the recovery from being dumped tree and another click to start the beam to user. The same panel, with the same panel, it is possible to get much more information than the previous one. It's possible to inspect the first layer of the subtree with all the subsequence. It is possible to go down to the tree up to check the state of the hardware connected to the logic of the behavior tree. There is a description on the right of all the tree. So, and in the bottom part of the panel collects all the settings made by all the nodes of the tree, and it is possible to filter out all the settings that do not match with the defined string. So this is my conclusion. There are more or less 1,000 of sequencer installed in Fermi and in the Electra Tango database. From the start, let's say, of the experiment, there were 8 people involved from controls, operators, and physicists. In operation in Electra since 2019, almost all the high-level applications in the control room are driven by the sequencer, except the ones used during the machine tuning. It was introduced, the framework was introduced in Fermi in 2021. So the developer doesn't have to care of graphical interface, log, and documentation because it is all provided by the system. The framework is very simple because it's based only on a Tango C++ server. If you want to build up more complex things, more complex trees, I suggest you to use also Qt Cumbia panels and the sequence template that is the implementation for BT structure. We have a short-term list. The first is a sort of versioning of the logic of an entire BT behavior tree logic, and start to do an offline analysis of the logs, which are quite massive, to detect anomalies in terms of execution time and the fault rate. Thank you.
Thank you, Giulio, for this interesting comprehensive talk about this new sequencer. We have some time for questions now. Please raise your hands.
I may ask one if no one else is there.
Yes.
Julio, you mentioned before that there were sequencers almost everywhere. It's a feature that all we need. So what was the process to choose these behavioral trees and not taking something else? I mean, out there are different solutions. And did you come up with a study of different possibilities, or you had this like a only idea and then you went for it?
In past, in 1997, something that looked not similar. So we have a previous experience at Electra of a framework that do some sort of automation. I have to be sincere, we didn't do a research for, and so there is no a previous study comparison between different types of implementation of the logic. So we choose the behavior tree without any theoretical study, let's say, before applying it on our machine.
And to which percentage you think that this development can be reused for any other, I mean, by any other institute?
Using the behavior tree, how fast how will we increase our productivity? Do you mean with the behavior tree?
No, I mean if I have to implement something by myself now, can I use yours?
It's Tango centric, but we can because you have the Tango database, which is we are quite tied with Tango. We have to do some work to make the tool more generic.
Okay, so I assume that for Tango users is off the shelf.
Yes,
reusable.
It's off the shelf, and there is nothing to install. You have just one server. There are no databases, nothing. It's very lightweight. I want to keep it because we have to use it in the next 10, 20 years. So less is better sometimes.
Okay. There is no space for other questions. So we can thank you, Julia, again, also for being in time. Okay, so our next speaker is Peng Su. Peng Su is an engineer working in the Dongguan Research Institute of the Institute of High Energy Physics in the Chinese Academy of Science. He's mainly engaged in the design and development of timing systems, fast protection systems, and fast orbit feedback systems. So Peng, if you are ready, you can share your slides and switch on the camera.
Yes, I share my. Okay. Okay, let's start. Hi, everyone. My name is Zhu Peng, and I come from the control group, the Dongguan branch of the Institute of High Energy, China. I'm very glad to share with you the states of the fast orbit feedback system for high energy photo source. I will present the detail on the design and the implication. Here is my outline. It includes the requirement, architecture, hardware and logic design, and so on. Okay, let's start. As we know that the size of the modern light source is getting small and small, and the brightness is getting higher and higher. So there are many BPM to monitor the orbit and many CREAT to create the orbit in the stone ring. Okay, this is a physical simulation feedback logic to the power supply for faster CREAT and working chain. In order to supervise the interface and keep beam orbit step. We adopt a high intent and the high speed orbit feedback system, or typical MIMO system. This is a BPM fast CRAT and vectory achievements. This is some important to affect the stable of the beam orbit. Commonly, we use to achieve the long-term step of operation of the high source based on the SVD. Here, there's a delta X is error that the current orbit is compared to the garden orbit. U and V are the matrix whose column is from the origin basically in the BPM and the correct magic theta space. S is the dialog matrix of the single values, and the PI control organized operates in this dialog space, and the event pyramid can be adjusted for each mode special. All those matrix and collocation stage are done at 1 BPM 1 FOLB cycle. So there is a requirement, and we should be considered about this. This is a necessary to comprehensive consider the whole time consumes, include the speed of the BPM data acquaintance, the delay of the global BPM data distribution and the communication, and other factors. According to the accelerator physical design and the requirement, the fast orbit feedback system should optimize stage to achieve the low latest response with BPMs and the fast power supplies, which is essential to achieve a center effective bandwidth run of the stable orbit. The main part of the HEPS is audio neural emission electrical stone rings composed of the 14/8 cells. According to the accelerator design, there are 20 BPMs and 8 fast correct power supply in each cell. So in the stone ring of the HEPS or kilometer scale ring, in order to reduce or over noticed and consider feasible study, we adopt the architecture of the tiny channel based on the 16 substation. Each substation is respond to interconnect with local BPM and the fast correct power supply, like this picture. Oh no. Each station is designed and the implication to obtain data from the BPM and in the SLPs and send the correct data to the fast correct power supply using a series point-to-point link. And each substation share the BPMs used in the FPS in order to ensure supplies with the global teams. All the above working squares is straight in according with the local in the global clock. For performance tuner and addition flexibility when end or remove BPMs or faster correct power supplies or load down new matrix. We use the inboard Ethernet controls is designed as a 4 hardwares use TCP IP approved international connect to the substation by using SPI. In pursuit of the support of the performance with the high-speed data transmission and the hardware system of the substation is only based ADC machine architecture, but customers the main logic back plant board and the series of the front board. For the substation hardware might include one main logic board, 4 front board for local BPMs, one of which is servers for the XBPMs, 1 front board for global BPMs, 4 front board for local faster corporation power supplies, 1 front board for global timing. The main logic backboard, the front board are using high-speed TE single connect to the interconnect mutuals and through the front board power supplies. A picture like this. This is my main, our main logic plan board. I have doubled the FPGA include V7, high-speed clock, LVDS, and the internet. This is a self-defined mind logic blackboard follows the ADC medical size is one of the core board of the FOLB. Consider the distribution and the renewability of the long-term operation and the for operate. So we dropped a large capital high density article. This is a PCB picture I have done. In the design of the PCB, we concluded the 2 things. First, one power integrates. We consider about such as the power stack and the deceiver division skewed corporate for current carrying rapid separation and other designs emerged under the consider of the transmission current. The first one, this is the second one, the singular integrate. We studied for the characters implication communication of the high-speed singers. We saw skewed return path rules is very important, nearby comprehension promise and the manual internet near switch. I have done some simulation. Okay, let's start the front board. The look from the look BPM date from the from board is my response for the connect 13.6 group of the effective dates and repeat about 2.3 GPS. The global BPM state from the front board is my response for the transmission BPM date connected by this substation to the global BPM data transmission link, and where is obtained other BPM substation, and the rate is about 10 GBS. The local BPM data from board and the global BPM data from board of the same hardware based on the ADC standard. And this is the input of the stable performance with the high-speed data transmission. The hardware system of the substation is only based on TCP ADC machine article, but customers the main logic board, the front, the fast craft.
Have 2 more minutes. 2 more minutes.
Okay. The data articles modules adopt our Pi9 designs, which is advanced that it can actually control the data to reach a central position at the time, reduce the delay all the time at same times. Because the amount of the permanent states then the system needed to store is very large, so it is necessary to call the black memory resource in the FPGA for data stores. Consider this design and global of the FOB no noticed. A block memory is used in the memory module designed to ensure that the data is read and write in one clock to reduce delay. This is a time commission estimation. Okay, this is not the summary. In order to reduce the system response time as much as possible and improve the effective feedback bank-wide of the FOLB system, we propose our new Harvard article that can quickly obtain all BPM states in the storm rings and quickly complete large data allocation and send the set to the fast correct power supply in real time. It shows that this article can achieve an effective bandwidth with more than 5,000 hertz, which also meets the MI requirement of the HEPS project. Thank you for all leaders and teachers, college of the research group of the HEPS, especially members of the FOLB. Thank you. This is my report. Thank you.
Thank you, Ben, for the presentation. We are running behind the schedule in time, so I still have one question on the chat. If you can go to the slide number 6. The question.
Okay.
The question is the DSP mean DSP IP cores inside FPGA or DSP processor?
Yes. Well, we use this pardon, I can't listen to the complete of your question. Please give me an.
Yeah, the question is that if the DSP that you mentioned there is DSP IP cores inside FPGA or DSP processor.
Okay, this here we use the FPGA is Xilinx V7, so the DSP is enables the FPGA.
Okay, I propose that we stop here because we are just 4 minutes behind schedule, and there is another question, but I will just redirect the question to you, and you can answer him in the WOBA. So we close this first session now. Tomorrow we resume with the second session of the feedback control, and we pass the relay to the data management session now in the same Zoom, or whether you want to attempt functional safety, you have to change the Zoom link. Thank you very much.
Thank you.